Introduction. Point defects in metals. Vacancies. Vacant atomic sites in a structure. Self-interstitials. Extra atoms positioned between atomic sites. In metals, a self-interstitial introduces relatively large distortions, strain in the surrounding lattice, since the atom is substantially larger than the interstitial site. Objectives. At the end of this lesson, you'll be able to correlate the density of a substance with its unit cell properties, describe the imperfections in solids and their effect on properties, correlate the electrical and magnetic properties of solids and their structure. Calculations involving unit cell dimensions. Suppose edge length of a unit cell of a cubic crystal determined by X-ray diffraction is A, D the density of the solid substance, and M the molar mass. In case of cubic crystal, volume of a unit cell is equal to A cube. Mass of the unit cell is equal to number of atoms in unit cell into mass of each atom, which is equal to Z into M. Here, Z is the number of atoms present in one unit cell and M is the mass of a single atom. Mass of an atom present in the unit cell, M is equal to M upon Na. M is molar mass. Density of the unit cell is equal to mass of the unit cell upon volume of the unit cell. Therefore, which is equal to Z into M upon A cube, which is equal to Z into M upon A cube Na, or D is equal to Z into M upon A cube Na. Imperfections in solids. Imperfection in the regular geometrical arrangement of the atoms in a crystalline solid. These imperfections result from deformation of the solid, rapid cooling from high temperature or high energy radiation, X-rays or neutrons striking the solid. Located at single points, long lines, or on the whole surface of the solid, these defects influence its mechanical, electrical, and optical behavior. Types of point defects. Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance, whereas the line defects are the irregularities or deviations from ideal arrangement in entire rows of lattice points. These irregularities are called crystal defects. Point defects can be classified into three types. 1. Stoichiometric defects. 2. Impurity defects. And 3. Non-stoichiometric defects. The stoichiometric defects. These are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. These are of two types: vacancy defects and interstitial defects. 1. Vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in decrease in density of the substance. 2. Interstitial defect. When some constituent particles, atoms or molecules occupy an interstitial site, the crystal is said to have interstitial defect. This defect increases the density of the substance. Frenkel and Scotty defects. Frenkel defect, shown by ionic solids. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site. It is also called dislocation defect. It does not change the density of the solid. shown by ZnS, AgCl, AgBr and AgI due to small size of Zn2+ and Ag+ ions. Schottky defect, vacancy defect in ionic solids. In order to maintain electrical neutrality, the number of missing cations and anions are equal. Decreases the density of the substance. There is one Schottky defect per 10⁻16 ions, shown by NaCl, KCl, CaCl and AgBr due to similar sizes of cation and anion. Impurity defects. When molten NaCl containing a little amount of SrCl2 is crystallized, some of the sites of Na+ ions are occupied by Sr2+ depicted in the figure below. Each Sr2+ replaces two Na+ ions. It occupies the site of one ion and the other site remains vacant. The cationic vacancies thus produced are equal in number to that of Sr2+ ions. Non-stoichiometric defects. If an imperfection causes the ratio of cations to anions to become different from that indicated by the ideal chemical formula, the defect is called non-stoichiometric. These are two types: metal excess, metal deficiency. Metal excess defect. Metal excess defect due to anionic vacancies. A negative ion may be missing from its lattice site, leaving a hole which is occupied by an electron, thereby maintaining an electrical balance. The trapped electrons are called F centers or color centers because they are responsible for imparting color to the crystal. Alkali halides like NaCl and KCl show this type of defect. Example: NaCl when heated in Na vapor, the excess Na deposits on the surface. Cl- diffuse to the surface where they combine with Na atoms which lose the electrons. The electrons diffuse into the vacant site created. The electrons absorb some energy from the white light and re-emit the yellow color. Metal excess defect due to the presence of extra cations at interstitial sites. Extra cations occupying interstitial sites with electrons present in another interstitial site to maintain electrical neutrality can cause metal excess. This defect is similar to Frankel defect and is formed in crystals having Frankel defects. Example: if ZnO is heated, it loses oxygen and turns yellow. The excess Zn2+ ions thus formed get trapped into the vacant interstitial sites and the electrons in the neighboring interstitial sites. It turns yellow when hot and white when cold. Metal deficiency defect. Metal deficiency defect due to missing of a cation of lower valency and presence of a cation of higher valency occurs when metals show variable valency. Example: FeO is mostly found with a composition of Fe 0.950. In crystals of FeO, some Fe2+ ions are missing, and the loss of positive charge is made up by the presence of the required number of Fe3+ ions. Electrical properties. Solids can be classified into three types on the basis of their conductivities. Materials that allow electrical charges to flow through them are known as electrical conductors. Silver and copper, graphite, solution of bases, ionized gases, etc. conduct electricity or called as conductors. Materials that do not allow electrical charges to flow through them are known as non-conductors or electrical insulators. rubber, glass, plastics, diamond, etc. are examples of insulators. Materials whose conductivity is less than that of the conductors and greater than that of insulators are known as semiconductors. Silicon and germanium are examples of semiconductors. Conduction of electricity in metals and semiconductors. The conductivity of metals depends upon the number of valence electrons available per atom. The atomic orbitals of metal atoms form molecular orbitals which are so close in energy to each other as to form a band. In figure A, if this band is partially filled or it overlaps with a higher energy occupied conduction band, then electrons can flow easily under an applied electrical field and the metal shows conductivity. In figure B, if the gap between filled valence band and the next higher unoccupied band, conduction band, is large, electrons cannot jump to it and such a substance has very small conductivity and it behaves as an insulator. In case of semiconductors, the gap between the valence band and conduction band is small in figure C, therefore some electrons may jump to conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature since more electrons can jump to the conduction band. Magnetic properties. The magnetic properties of materials are consequences of magnetic moments associated with individual electrons. The magnetic moment of an electron is due to its orbital motion and also due to its spin around its own axis. A moving electron may be considered to be a small current loop generating a small magnetic field which has a magnetic moment along the axis, and the magnetic moment due to electron spin is directed along the spin axis. The fundamental magnetic movement is the Bohr magneton, MB, which is equal to 9.27 into 10 raised to the power minus 24 am square. Types of magnetic properties. On the basis of their magnetic properties, substances can be classified into 5 categories. 1. Paramagnetic. 2. Diamagnetic. 3. Ferromagnetic. 4. Antiferromagnetic. And 5. Ferrimagnetic. Paramagnetic substances are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. Paramagnetism is due to presence of one or more unpaired electrons which are attracted by the magnetic field. O2, Cu2+, Fe3+, Cr3+ are some examples of such substances. Diamagnetic substances are weakly repelled by a magnetic field. Diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of electrons cancels their magnetic moments and they lose their magnetic character. H2O, NaCl, and C6H6 are some examples of such substances. Antiferromagnetism have domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other's magnetic moment. Substances like MnO showing antiferromagnetism. Ferrimagnetism. Ferrimagnetism is observed when the magnetic moments of the domains in the substance are aligned in parallel and anti-parallel directions in unequal numbers. They are weakly attracted by magnetic field as compared to ferromagnetic substances. Fe3O4, magnetite, and ferrites like MgFe2O4 and ZnFe2O4 are examples of such substances. Did you know volume defects are three-dimensional in nature? These defects are introduced usually during processing and fabrication operations like casting, forming, etc. Example: pores, cracks, foreign particles. These defects act like stress raisers, thus deleterious to mechanical properties of parent solids. In some instances, foreign particles are added to strengthen the solid dispersion hardening. Particles added are hindrances to movement of dislocations which have to cut through or bypass the particles, thus increasing the strength. Summary. Let us summarize what we have learned. There are different types of imperfections or defects in solids. Point defects are of three types: stoichiometric defects, impurity defects, and non-stoichiometric defects. Vacancy defects and interstitial defects are the two basic types of stoichiometric point defects. In ionic solids, these defects are present as Frankel and Scotty defects. Solids show many types of magnetic properties like paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism.